In this video, I will be using the equations I derived in part 1 to simulate the changes in concentration and temperature for this continuously stirred tank reactor when the cooling temperatures changed from 300 Kelvin to 290 Kelvin and when it's changed from 300 Kelvin to 305. So first I have here the import statements I'll be using. I have imported NumPy and solve IVP from SciPy integrate. I have also integrated plotly.subplots, make subplots from plotly.subplots to plot the behavior of the concentration and temperature, as well as plotly.io to change the background of the plot to dark. So we're going to start by putting in all of our constant values that are given here. So I'm going to start with Q. It's equal to 100 liters per mole or liters per minute. The concentration in is 1 mole per liter. The initial temperature is 350 kelvins. The total volume in the tank is 100 liters. The density is 1,000 grams per liter. The specific heat is 0.239 joules per gram Kelvin. The E over R, which I'll just call ER, is 8,750 Kelvin. The rate constant for this reaction is 7.2 inverse, or 7.2 times 10 to the 10th power inverse minutes. The heat transfer constant times area is 5 times 10 to the 4th, and that is in units of joules per minute times Kelvin. And then the enthalpy of the reaction is 5 times 10 to the 4th joules per mole. So now I'm also going to put in our initial concentration, or the initial coolant temperature, the initial concentration of the tank, and the initial temperature in the reactor. So TC0 is 300 kelvins. The concentration of A initially is half a mole per liter. And the initial temperature in the reactor is 350 kelvins. So now what we need to do is we need to define the right-hand side of our equation to be able to solve it using solve IVP. So solve IVP always takes temperature as the first input, and then we will have a vector of our unknowns. We can go ahead and unpack this vector. It will be our concentration and our temperature. And then we also need, if you look at the equations from the last part, both of these depend on K, which is an equation that's dependent on time. So I'm going to go ahead and code the equation for K in there. Which is ER negative ER over T. And then I will code our differential equation for concentration, which is our flow rate divided by the volume times the concentration in minus the concentration of the tank minus the rate constant times the concentration of A. And then if you look here for this equation, we need to get the rate of change of temperature over time alone by itself on the left-hand side. So I'm going to divide by rho, the volume, and the specific heat. So I'm actually going to move my window down a little bit so I can do this. And so it will be, for the first term, it will be Q over rho, because volume and specific heat will cancel out. This will be multiplied by the temperature in the tank, or the temperature going in minus the temperature of the tank. And then again, for the second term, dividing by the density times volume times the specific heat capacity. The volume will cancel out, so I'll get the rate times the concentration of A divided by the volume times the specific heat capacity. Or no, the volume will cancel out, so it'll just be the density times the specific heat capacity times the enthalpy of our reaction. And then again, dividing by the density, volume, and specific heat. It's just that term for the heat being transferred from our reactor to the coolant, divided by those three variables. And then this will be times the temperature in the tank minus the coolant temperature. So now I have an error here. It says this should be Tn. And then we need to provide the coolant temperature. So for the first case, we are simulating a change from 300 Kelvin to 290. So our coolant temperature will be 290 Kelvin. So now we can use solve IVP to solve our right-hand side. So we'll pass it our function, followed by our time range, which will be 0 to Tn, followed by our initial values, which is the initial concentration and the initial temperature. The method will be Radow, and we will set dense output equal to true so that we can evaluate this at any point and plot it in our graph. So I'm going to go ahead and define our simulation end time. We'll run it for 10 minutes. So let's go ahead and see if this works. I have an error. Forgot to run the first block, so now this should be good. Nope, we still have an issue. All right, so I found my error. I forgot to put a comma in between our two equations, and I was missing a multiplication sign right here. I've added those in, so solve IVP should work now, and it does. So now we're gonna go ahead and grab the solution object using .sol, and I'll set it equal to our solution. So now we are ready to graph these two equations. So first things, I'm going to create a variable of time for our plotting purposes, and I'll do that using numpy.linspace. And I'll start at time equals 0 to the time of our end simulation, and I'll do about 150 data points. So now I'm going to pass this variable to our solution, And if you notice, we have two separate arrays here. This first one is our concentration values, and the second one is for temperature. So I'm going to go ahead and unpack these. And now we're ready to create our graphs. So figure 1 will be make subplots. And I'll graph these next to each other. So we'll have one row and two columns. So now I'll add our first scatter plot. The x variable will be our time for plotting purposes. The y variable will be our concentration. I will set the mode equal to lines. I will name this CA for our concentration of A, and we'll put this in row 1 and column 1. And so then I'm going to copy this and do the same thing for temperature. So instead of concentration, it's temperature. We'll adjust the name to reflect temperature, and then I'll put it in the second column. So now there we go. I'll make this a little bigger. Here is the dynamics of our reactor. So as you see, concentration steadily increases and reaches steady state, and the temperature decreases and also reaches steady state. So now I'm going to manipulate this. So instead of decreasing our coolant temperature from 300 to 290 Kelvin, I'm going to increase it from 300 to 305 and see what happens. So now we get loads of oscillations in here. So even the small amount of change in temperature of the coolant can have a big effect on the reactor. Even just 5 degrees Kelvin causes this reactor to behave very almost volatilely and cycles. The concentration of A rises and then drops again, and the temperature will drop and rise with the concentration.